Okay, last one for today. This is again for IM2. We are transforming functions. Now we're specifically focusing on quadratic functions, parabolas, but this concept works for all functions. So I'm trying to speak in very general forms, in a very general way, so you can apply it to all kinds of functions that you'll see for the rest of your life. Um, yeah, however long you might be studying transformations of functions. But anyway, generally speaking, if you add or subtract, but subtracting really is adding a negative, adding or subtracting will cause a shift. Okay. So when you hear the word add, that means shift. This is a rigid transformation. Doesn't change the steepness or doesn't change the shape. It just shifts it around. Multiplying, anytime you multiply or divide, and again, dividing for me, I like to think of it as multiplying by a fraction. That'll cause a stretch. So a stretch, any kind of a change in steepness, is going to be caused by multiplying. And whether it's a compression is also a change in steepness, or a stretch is a change in steepness. Um, eh, how you name it, it depends on where you're multiplying. So we'll look at a little bit about that. Anytime you multiply by a negative number, it's going to be a flip. Okay, so you might flip it horizontally, you might flip it vertically. You've seen parabolas that were flipped vertically before. You've seen uh, most of the functions you've studied so far. Flipping it horizontally hasn't made a big difference. It looks the same, but you will look at other functions later on that it does make a difference if you flip it this way. And then if you add, or this is another general rule of thumb, if you add or multiply to x, you will cause some sort of a change in the x direction, some sort of a horizontal change. If you add or multiply to the function, so after you've already calculated, you've already plugged x into the function, then you multiply or you add after that, it's going to cause some sort of a change in the vertical direction, in the y direction. So I've got some examples here that we'll walk through, a few Desmos examples of doing each. So this is adding to the function. So this is adding after you have plugged x in. So I've got a function here, f of x equals x squared. I have g of x equals f of x plus k. So I've already calculated my value for the function, then I'm adding k. If you look, the red graph is the original graph, and the blue graph is after I add k. Right now I'm adding -6 to it. If I add -5 to it, it's shifted. It's still shifted down. It's not actually changing the shape. This is adding 0. This is adding 1, adding 2. All it's doing is it's taking every point on this graph, like this point here, 1, 1, and it's shifting it up 2 units. So this graph is going to have the point 1, 3. If the original graph has 2, 4, this new graph is going to have 2, trust me, oh wait, here, there we go, 2, 6 is going to be on the new graph. Every point on this red graph is shifted up by that amount. Adding causes a shift. Adding after I've calculated the function will cause a change in the y direction. Okay, here is an example of me adding to my x value first and then plugging it in. Okay, there we go. So we have, so I want to turn this one off. I want to turn this one on. So this is me adding a value, h in this case, adding h to x and then calculating it. And notice what happens as I change h. It shifts it right or left. It is a shift. So this one here is me subtracting a -5. You might think of subtracting a -5 as actually adding 5, because they'll have the same result. So f of x plus 5 shifted my red graph 5 units to the left. And the bigger negative number that I subtract, so basically this is f of x plus 10, it shifts it further and further left. F of x minus 10 is shifted 10 units to the right. Okay, so this is me adding to x, then plugging it into the function. So where I'm adding makes a difference. Here is an example of me multiplying with x first. So this is really, really tricky. So again, I'm gonna turn this one off. I'll turn this one on down here. So notice I'm taking whatever b is and I'm multiplying b times x, then I plug it into the function. And I wanna turn this equation on as well, y equals 4. So what you'll notice is, so here's the original graph. The original graph has the point 2,4. B is 1/2. So what this means is the first thing I'm going to do is multiply the x value by 1/2, take half of it, then plug it in. That forces, this is really, really tricky and very subtle, that forces all of my x's to be bigger numbers to have the same outcome. So if I'm going to take half of x and then plug it in, this point here is now shifted to 4. Same y coordinate, but I need an x value that's twice as big. If I move this up to 9, 9's a nice convenient number because it's perfect square. So here, this is 3, 9. This one is going to have to be 6, 9. It has to be twice as big because the first thing I'm going to do is cut it in half and then square it. So it forces all of my x values to be twice as big. If I were to make this 1/10, then all of my x values have to be 10 times as big. Let me move this down a little bit. Let me move this back down to 4. Oops, to 4. There we go. And let me scooch on over here a little bit. Let me zoom out. So here, so b is 1/10. So this says, first thing I need to do is take 1/10 of x. So it forces all of my values of x to be 10 times bigger than they were before. 2,4 was on my original graph. Now I need to plug in 20 because then I'm going to take 1/10 of it and then square it. So when I multiply times x, it changes the graph in the x direction. And it has this weird effect of, let me multiply by 2. Really weird. Multiply by 2. Basically, what that does is forces all of my x values now to be half as big as they were before. On the original graph, 2,4. On this new graph, 1,4. My points can be half as big because the first thing I'm going to do is double them, then square them. So it forces all of my x coordinates to be half of what they used to be instead of 2 times. So this one for students is like the hardest one. But just think of it as has the opposite effect. It forces my x's to change. So this has a horizontal change. When b is greater than 1, it compresses it horizontally because my x values can be smaller because the first thing I'm going to do is multiply them and then, in this case, square them. Okay, and if it's a fraction, then my x values have to be bigger, because the first thing I'm going to do is multiply them by that fraction and then square them. So it forces my x values. It stretches it horizontally. Really kind of subtle and strange. And this last one is not very difficult for most students. This is when I multiply the function. So after I've calculated the value. Let me scooch on over here a little bit. Turn this one off, and I got this one at the bottom, way down here. Oh, I don't. That's right. It's kind of a weird thing. So let me change this to x equals. And let me move my b from there to here. I'll put it in front. And let's graph this one. So now what happens is, so my original graph is y equals x squared. And let's graph x equals 4. So for this one here, x equals 4. And then notice, so I'm multiplying out here, and it's half. Okay, so I'm going to go to my original graph. My original graph had the point 4. I bet you could predict 4, 16. Well, now this takes every point on this red graph and it multiplies them by 1/2. So now 4/8 is on that new graph. Um, and it happens for every value of x. I could do x equals 2, for instance. So 2 on the original graph, 2, 4. On the new graph, 2, 2. Because every single y coordinate is cut in half. This is multiplying my y coordinates, and it's multiplying them by 1/2. If I were to triple it, then on the original graph, 2, 4 is on here. On the new graph, 2, 12. It took every point on this red graph and it stretched them all 3 times farther away. It made all of their y coordinates 3 times as high. So it's a vertical stretch. Okay, so we have a couple others. I'm going to go ahead and stop the recording right now, though. You don't need to know that.